much. It's a pleasure to be here again, and I'd like to thank the organizers in the first instance for the invitation. So this is going to be a talk based on the master's paper of my student who is here. So I'm Tevian Dray.
And I'm Lida, Bentz.
And we're going to split the talk, so about Split Octonions. So I'll go first and I'll tell you a little bit about the background of the Split Octonions, and then Lida's going to tell you something about the classification of the subalgebras. So let me start by reminding you about what a composition algebra is. The important property is here that you have a notion of a squared magnitude, which is multiplicative, that the norm of a product is the product of the norms. But we are not assuming, as most people do, either that the underlying algebra is associative or that that norm is non-degenerate. You'll see why in just a moment. It's well known that any such composition algebra that has a unit element can be obtained from the Cayley-Dickson construction, which I'll briefly go through and show you the sort of standard cases, which of course includes the Quaternions. The Cayley-Dickson process says if I start with an algebra, so A and B are elements of some algebra, I can take pairs of elements in the algebra and turn, if you like, the square of the algebra into an algebra of its own. But I have to tell you how to conjugate, multiply, and take the norm of elements of the new algebra, which you can think of as being k plus k. So ordered pairs of elements in the algebra. And if you think about this process, this is just a formalization of the way you already know how to get from the reals to the complexes by adding another copy of the reals multiplied by I, or from the complexes to the Quaternions, again by adding another square root of minus 1, typically called j. And of course there's a third. Continuing down this path, there is another such algebra, the Octonions, which you get in exactly the same way by taking two copies of the Quaternions, adding yet another square root of minus 1. And so you have, starting from the reals, the two-dimensional, as a vector space, two-dimensional complex numbers, four-dimensional Quaternions, or eight-dimensional Octonions. I would like to emphasize that little thing I just mumbled about vector spaces. We're talking about algebras here, and there's a little bit of confusion in the language. When we write direct sums, we will always mean of the underlying vector spaces, but our multiplication tables will always be set up in this other way. It's not a direct sum of algebras. Anyway, here is, for those of you who might not have seen it before, or possibly if you have, the nice encoding of the multiplication table of the Octonions. The Octonions are not associative, they are alternative. The Quaternions, of course, are not commutative, but are associative. And this is an ordered copy of the 7-point projective plane, the Fano plane, showing how to multiply the 7 independent, linearly independent square roots of minus 1, where each of these lines is, of course, like a circle. One of them is shown as a circle. Each of those lines represents a quaternionic subalgebra of the Octonions. Let me pause there and ask if there are any questions so far. Hopefully this is pretty standard stuff so far. Okay, so if you notice in the Cayley-Dickson construction, there's an epsilon here. Each time you add a new unit in the Cayley-Dickson process, you could do as we've done here and add another square root of minus 1. But you could instead add a square root of plus 1. And those are the only choices. There's a theorem, the Hurwitz theorem, which says that if you want the norm to be positive definite, then the choices I've already shown you are the only possibilities over the reals. The reals, the complexes, the Quaternions and the Octonions are the only real composition algebras with positive definite norm. But if I start adding something which squares, so epsilon being minus 1, that is a weird convention because that means it squares to plus 1. If I add, I'll call it capital L to the reals, complexes, or quaternions. Where capital L squares to plus 1, I still get a composition algebra out of the Cayley-Dickson process, but it does not have a positive definite norm. Lida will tell you more about the signature of that inner product in a moment. And other things happen that you're not expecting, as it should be expected from the fact that we don't have a positive definite inner product. The magnitude of this capital L is -1. It has negative squared norm. Unfortunately, that's the way the language goes. So the norm is a quadratic thing, so we continue to call it the squared norm, but it's negative. Even though the element itself squares to +1. And on top of that, you have elements like 1 plus L. We can actually think about this sort of like special relativity and hyperbolic geometry, if you know anything about that. You have elements that are null. This is like adding a time-like direction into your vector space. Now you have space-like and time-like directions. So of course you also have null directions. And if relativity doesn't speak to you, don't use that analogy. But if it does, you might find it helpful. So there are both null elements and things with negative norm. The inner product, however, is not degenerate. Okay? It's still a non-degenerate inner product, it's just not positive definite. Here is, for completeness, the full multiplication table of these split octonions. It does not have a nice representation like the Fano plane, the 7-point projective plane, because the signs, of course, have changed. You've got, elements squared to -1, elements squared to +1. And there's 4 of each. Okay. All right. Sorry, one more slide. Some properties of the split octonions. You have 3 non-real unit elements that square to -1 independent, but the other 4, we of course ran out of letters, so I, J, K, L, and the other 3 are I, L, J, L, K, O. There are 3 still 7 square roots of plus or minus 1, but only 3 of them are imaginary, if you will, square roots of -1. The other 4 are hyperbolic, they're square roots of +1. It is still an alternative algebra, just like the octonions. There are idempotents. That null element I showed you, 1 plus L, squares to itself up to normalization. There are also nilpotent elements. K plus or minus KL squares to 0. So you have to deal with both idempotents, nilpotents. Both the idempotents and the nilpotents are null. But it is still a composition algebra. And in particular, if you take a null element whose squared norm is 0, and you multiply it by anything, the result is also a null element, because the product of the norms is still the norm of the product is still the product of the norms. And so if one of the elements squares to 0, when you multiply by anything else, it still squares to 0.
All right, so now we get into signature. So the signature of a composition algebra we define to be the triplet here, where P are the number of positive norm, squared normed elements in your orthogonal basis, M are the negative normed elements in your orthogonal basis, and N are the 0 normed elements. So if we look at some things we know, we have the complexes would have signature 2, 0, 0. Quaternions 4, 0, 0, octonions 8, 0, 0, and then we get into the weird stuff. We have the split complexes have signature 1, 1, 0. Split quaternions have signature 2, 0, 2, 2, 0, and split octonions have signature 4, 4, 0. So we also note that our signature, if we add up each number in our triple, we will get the dimension of our space that we're discussing. Okay, no, too far. All right, we're going back to the arrows. All right, so there we go, beautiful. So because we have these 0 normed elements, we have 0 normed elements, we end up with null subspaces. So a degenerate subspace of any particular subalgebra is going to be the set of elements that are orthogonal to every other element in that subalgebra. As we saw, because of the composition algebra piece, the null elements of your subalgebra will close under multiplication. And indeed, they will, in fact, be, if they close under multiplication, then they will be an ideal of your subalgebra. So let's look at some examples of this. So we have the one-dimensional cases, of course, the real line, signature 100. We cannot have a signature of 010, because as soon as you have one of those time blank elements or something like with L in it, L squared will be 1, and we don't, the signature would then not work. But we can have signature 001. We can do that with an idempotent element, with something like 1 plus L, or 1 minus L. And we can also do that with our nilpotent elements, so things like K plus KL, K minus KL, I plus IL, I J minus JL. So from here, we started by looking at the 1D, and then we built our way up. So then we look at our 2D subalgebras. So signatures that add up to 2. We have the complexes, we have the split complexes. But we also have, we can take our smaller subalgebras and tack on, where appropriate, either a nilpotent or idempotent element to our generating set. So, for example, we have signature 101, where we have the real line summed with the nilpotent element K plus KL, or K minus KL. And we can also extend our signature, so we have 002 signature. So we can take an idempotent element with a nilpotent element and produce the signature, as well as 2 nilpotent elements. So building our way up, here was our 2D. Moving up, we can then look at our 3D subalgebras. So we can have signature 003. Again, we can take an idempotent element and tack on a 2D degenerate subspace, and this will create a signature we want, or we can create a completely null subalgebra with I plus IL, J plus JL, or K minus KL. Then we can also take the real line and tack on a 2D degenerate subspace, and that's how we get something like 1, J plus JL, and K minus KL. And then turning to the split complexes, which have signature 110, we can take that and tack on K plus KL or K minus KL. So that way the multiplication by L isn't going to get you out of your space. These are known as the Quaternions. So then, continuing our way up, we get to our 4D subalgebras. Again, we have a couple we know in the Quaternions and the split Quaternions. But we can also look at taking our idempotent element and summing our 3D degenerate subspace. So we have 1 plus L, I plus IL, J plus JL, and K minus KL. Similarly, building, we can start with the reals and then tack on a 3D degenerate subspace. So we have 1, I plus IL, J plus JL, and K minus KL. And then we can take the complexes and tack on a 2D null subspace, similarly with the split complexes. And actually, we can go higher than 4D. Not much higher, but we can. So the only 2 other signatures we have in higher dimensions, aside from the entirety of the split octonions, would be signature 113. So we're taking the split complexes and we are adding a null 3D subalgebra. So I plus IL, J plus JL, and K minus KL. And then high as we can go would be signature 222 with the Sextonians. We take the split Quaternions and we tack on a 2D null subalgebra.
So what Lida has done is hopefully given you a very good sense of what was done in practice by her. Proof by exhaustion. Consider all the possible signatures and see whether there is a subspace with that signature. And what you saw on the first slide was an example that didn't work and why it didn't work. The rest of those were left off of these remaining slides, but there are analogous elements that show that all the cases that you didn't just see fail. They don't close for some reason, or they lead you, when you form the algebraic closure of your generating set, they lead you to one of the other cases. So now we can look back and say, what do these subalgebras look like in the sense of what are their common features and properties? And so here's what has in fact been proved by exhaustion, which is that any of the subalgebras of the Split Octonions can be written as a vector space, as a direct sum of two pieces. One, so it's an orthogonal decomposition where one of these spaces is degenerate, totally null, all dot products, if you will, or zero in that space. And everything in that space n is orthogonal both to everything else in n, but also to everything in x. Okay, so totally null piece and a piece that you're used to. And furthermore, the null piece is an ideal. And so all of the subalgebras start with the reals complexes, Quaternions, well, Octonions aren't there, or the split complexes, split Octonions, and add one of these null subspaces to it that's orthogonal to it, and that's it. You can do that in all possible ways, and those are the only things you can do. Okay? And an immediate corollary is that these simple subalgebras of the split Octonions, so the ones that don't have proper ideals, are of course the reals, complexes, and Quaternions, also the split Quaternions and the split Octonions, but also the one-dimensional null degenerate subalgebras, because they're one-dimensional, you don't have proper null, proper ideals. But interestingly, the split complexes are not simple. If you think about it in terms of Minkowski space, again, to use a relativity analogy, the two null directions form a decomposition of that space, which gives you proper ideals, okay, because they're each null. So here at the end of the day is a full table of all of the possible cases on one screen, all of the possible signatures, and how they are put together as our notation is we've given names to all of these building blocks, the idempotent and nilpotent and other null subalgebras, and then everything else is just as a vector space a direct sum of those choices, together with an explicit generating set in the split Octonions. So that's GIG. There is the answer. There are a lot more subalgebras of the split Octonions than you might have thought, including 5- and 6-dimensional ones, which was a surprise to us, as well as 3-dimensional ones. Hamilton, as I'm sure you know, in finding the Quaternions, was trying to find a 3-dimensional algebra, and there wasn't one. We've got 3, okay? So in that sense, the split Octonions are special fun and surprising. Thank you.
Okay. Anyone have any questions for the speakers?
I'm wondering, if I fix a signature, how many examples are there of exhaustive examples?
So what, I'm not sure I'm understanding the question.
I'm fixing a signature, say 003.
Okay.
We're listing 3 subalgebras. Are
No, so again, we've used an explicit basis to help us coordinatize things, but you basically have two choices. It's split octonions, you have 4 orthogonal planes, if you will, each of which is a Minkowski space. And you take one null vector from each of those 4 planes. And that's the only thing you can do. And so now how many ways can you choose? However many vectors, I think you chose 3. 3 vectors from 4 things, well in principle there are 4 ways you could do that depending on which one you left out. But you're either leaving out a nilpotent element, which you could do 3 ways, or you're leaving out an idempotent, which you can do 1 way. The 3 collapse to be 1 example. And that's the argument that there are 2 examples of signature 1, 1, 1, and it goes through similarly for the other cases.
Well, I was just thinking about, so when, like, Hamilton wanted a 3-dimensional algebra, we wanted everything to be invertible, right? And we don't have that. But there's this idea that this interpretation using relativity where you have like left vectors. So does that lend itself well to the geometric interpretation?
So certainly the 1-1 case, C prime, the split complex number is absolutely a wonderful algebra to use to describe special relativity, 2-dimensional special relativity. It's not usually described that way, but it's a great way to do it.
What about like other 3-dimensional geometries, like solid geometry?
I don't have a good answer for you. Certainly you could do, I mean the problem is to do relativity you want Lorentzian signature, these splits that tend to have the same number of space-like and timeline corrections. There are people who try and do physics with climbing and metrics, which have signature 2, 2. I would guess the split quaternions are the right language for that, but I don't know enough about that approach or those geometries to give you a better answer.
Any other questions? Okay. Now let's have a little break to our next speaker. And let our next speaker set up. And the next one will be 2.
We finished on time.
You were perfect. Okay. Whenever you want to, this is like
2:45, it's just 5 minutes.
Okay, so should we wait?
Yeah, I think we should wait.
I think we have to wait because of the
Okay.
multi-schedule.
Okay, yeah, because, okay, so we have about a 15-minute break.
Just a quick side question while we
Okay.
wait.
Yeah, sure.
Any association to partitions of integers?
Only in the sense that, of course, we had to consider all signatures, and in that sense, we're partitioning the dimension of the space, but
No.
not really, no.
Do you know anything about this?
Yeah, sorry for you.
Just wait 5 minutes.